So in this video, I want to talk about the insurance problem from the consumer's perspective. And the setup is similar to what we've been talking about. So what we want to remember from our very first video when we talked about uncertainty, what a consumer cares about is its expected utility. So it's a weighted average of the utility. So you have one utility here on a bad state where I'm going to suffer a loss. This is the probability of a bad state. 1 minus p, this probability of a good state, and that's the utility that I'll get. That's the common setup. Now, the main variable of interest, of course, is the x, okay, which is the amount of insurance that I'm going to purchase. Okay? And provided that this utility function is concave, which for most of your problems it will be, then the expected utility function is a sum of concave function. Then the whole thing will be concave. And therefore, we're going to have a concave objective function. So the first order conditions are both necessary and sufficient. So we're going to take a derivative of this with respect to x. We're going to apply the chain rule. Note, I'm doing this for the general case, but the utility function is not known. But remember, we're dealing with concave utility functions because we're assuming that the purchaser of insurance are risk averse, and they have to be. Otherwise, they would not purchase insurance. So let's take the derivative. P times u prime of the consumption in the bad state times the inner derivative of this, which is with respect to x, which will just be minus q, which is the price per unit of insurance, plus 1 minus p times u prime, consumption in the good state. Note with this consumption in the good state and bad state, I'm just being a bit lazy, so I don't have to write that up, but it's also a bit clear to kind of visualize what's going on here. Times minus q, and of course I made a mistake here. Can you spot my mistake? So I did a derivative here, and of course this cannot be the same, but when I did this derivative here, I forgot this x here. The derivative of that would be 1. So it would be 1 minus x, minus q, 1 plus q. All of this will equal to 0. And remember, because we're dealing with a globally concave function, this solution is both, this condition is both necessary and sufficient, okay? And we know that the value of x will affect both the consumption in the good state and the consumption in the bad state. If I have the value of x, I have everything else. I know the wealth, it's a parameter given to me. I know the loss, it's a parameter given to me. I know the q, it's a parameter given to me, so I can find everything. So if I rearrange this, I will find that p times u prime in the bad state over 1 minus p u prime in the good state will equal to q over 1 minus q. And I like to write it this way precisely because this thing here is the marginal rate of substitution for consumption in the bad state and consumption in the good state. Okay? And this thing here is the relative price of consumption in the bad state in terms of consumption in the good state. Okay? So this is the marginal rate of substitution. This is the optimality condition. Okay? Now, this is the consumer problem. Note one special case. What if P is equal to Q? And this is the definition of actuarially fair insurance. So if the probability of loss is 70%, then the premiums that you will get charged will be 70 cents per every dollar that you pay out. That's an actuarially fair insurance. Well, if that happens, then when I duplicate this, well, those things are the same. So if that's the case, this will cancel with this will cancel with this, and the optimality condition would be u prime of CB must equal to u prime of CG. Well, if you think about the utility function as being a strictly concave function that increases in the money or in the consumption that you have, it's strictly concave, which means there is only one way that the derivative of CB can be equal to the derivative of CG. That can only be if CB is equal to CG. Okay, so what you're saying is that that is exactly the definition of full insurance. You're fully covering for the loss, right? And therefore, this example shows the general first order condition for the general insurance problem, and a special case when the insurance problem is where the insurance itself is actually fair, showing that a risk-averse individual, regardless of the utility function, as long as it is concave, right, the definition of risk-averse, they will fully insure. I hope you find this video helpful. I'll see you on the next one.